So I'll just start by very briefly reviewing Gaussian processes, because we're going to make a fair amount of use of them today, and they will form the basis of a lot of the conditional modeling that we'll be doing over the next few weeks. So the idea is really very, very simple. We just assume that we have some random variables which are jointly Gaussian, and if they're jointly Gaussian, then, well, we can actually estimate, one derivative and the other fairly efficiently. Like, for instance, let's say the weight, the height, metric units. If you can squint and see that's 100, yeah, 100 pounds would be a little bit light. But basically, what you can do here is you can then estimate, p of weight given the height, just by taking the joint, dividing by p of height. But since I already know p of height, so I only need to know that functional form, and that means that all we need to do is look at this equation here and tease out all the linear and quadratic terms in x2. Because if we know all the linear and quadratic terms in x2, we can just figure out the normalization anyway, so we don't even need to compute the rest. It just makes our life a lot easier. And then, well, at some point, if you want to actually compute, or imply vector, random variables t and t prime things, and then of course normal distribution, we can actually estimate t prime given t. And so you pull out all the terms, and you'll see that the covariance in the t primes is reduced. So this was the original covariance, and now it's reduced by how much the t's and t primes are correlated and how noisy the t's are. And the mean is slightly shifted, and it's shifted in accordance to how much t actually deviates from its expected value mu, and how strongly correlated t and t prime are, and how noisy t is in its own right. And the nice thing is that you can basically define what's called a Gaussian process. So instead of just a fixed set of random variables like height, weight, age, whatever, you can just have an entire index set and define things over that. And, well, that's exactly the definition of a Gaussian process, namely a stochastic process with a property that for any finite dimensional draw from that process, the random variables are jointly Gaussian with some mean function mu and some covariance function, well, given by k. And then we made the connection to kernels, and we're going to do a lot more kernels later on. Now, the first obvious thing is, you can just do regression, and that's what we already saw before. Remember, these were the equations here. And if you squint at that, you can actually see that this is basically just a linear regression model, right? So I can go and pre-compute this term here, because this only depends on t and mu. So this gives me, in other words, a vector. And now this term here is a matrix, where I'm feeding in the t's and the t primes. So in other words, the entries of this matrix are going to be of the form k of xi prime xj. Right. The xij are going to be in the training set, and this is going to be in the test set. Right. So in other words, for a specific coordinate in t prime, this is just going to be a linear combination, sum over j, some coefficients beta j times this expression here. So what we've done is we've just moved from a simple linear regressor to non-linear regressor, and we have done so fairly effortlessly by just playing with Gaussians. I mean, this is basically undergrad math if you think about it. I mean, in which year did you learn normal distributions? Year 1? Year 2? Year 3? Okay. Wow, that comes late. So what it really means is that by using very, very elementary tools like a Gaussian, we managed to actually come up with a regressor that's pretty much state of the art. And, and we have some kernels, and we're going to look at them a lot more. one interesting case was, of course, if we have a linear kernel, right, then this thing becomes, you know, k of x and x prime is x of x prime, and just plugging in all the terms gives me this expression here. So that's really just, you know, working out the linear algebra. It's exactly the equation that we had before in history. Now, this equation is kind of cute, but unfortunately it's also very disturbing. Okay, so if you squint at that, you see that for the covariance on unseen data, it's basically x prime transpose, then here it's identity matrix minus the projection onto the space spanned by the x's times x prime. Okay. And, well, this is a huge problem because as soon as the x's span the entire space, this becomes the identity. So I get that my predictive covariance is 0. Which means I ridiculously underestimate the uncertainty in my observations. And so I'm basically becoming very blinkered by just saying, well, I already know what the future is, so no need to see any more data. I know with certainty what I'm going to see. Now that, in reality, is complete garbage, so you need to fix it. And the issue is that if you have a linear Gaussian model, right, so it's a Gaussian process with a linear kernel, and you draw from it, yes, of course, you would be in a linear, in you know, a low-dimensional space. So if I have d dimensions, then after seeing d instances, I will have entirely determined that process. Then I know it. Then I've basically reduced all the variance. So what's going on? Well, what's going on is that I'm actually not really observing the draws from that Gaussian process, but I'm observing those draws with some noise added. So for instance, if you were to build a standard linear model, you would say, well, actually, I guess this is pretty much what the data looks like, but since I'm not quite sure, I'm going to add a little bit of noise to it. Right? And the problem is that we failed to do that in our case. So, you know, in high dimensional, high dimensions, I mean, that's what it looks like. So let's say in 3 dimensions, this is essentially a disk, right? So you have like one direction of significant variance, second direction of less variance, and the third direction is just completely flat. And so the bad thing is, it also means that if you then observe something that's not on that plane, its likelihood is 0. So your model just doesn't work. So does anybody have an idea of what one could do in order to fix it? By the way, looking ahead at the next slide does not count. Anybody has an idea? Well, we add some noise to it, right? So what I'm assuming is simply that I don't have that y equals, you know, t of x, you know, in it. But I'm assuming that I have this plus some noise. And I'm assuming that this noise is drawn from maybe a normal distribution with 0 mean and variance sigma squared. Now, what happens is that the y's, in this case, are not just drawn from, well, I mean, the good thing is I'm adding 2 Gaussians, right? We know this is normal, we know this is normal. The sum of 2 Gaussians is a Gaussian. So therefore, and even more so, we can figure out the mean and covariance by just adding them up. Now the mean here is 0, so the mean, so remember, this was drawn from normal distribution with, you know, x transposed, and some mean mu. So now, you know, the sum over those 2 random variables is going to be drawn from a normal distribution with some mean mu, 0 plus mu is mu, and covariance x transposed plus sigma squared times the identity. So I take my covariance matrix, which is low rank, it's x transpose, and I add to that a diagonal matrix which has the value sigma squared on the main diagonal. Right? And that, of course, makes the problem go away. Because now this matrix here has full rank regardless of how many x's we observe. So what happens then is that this equation here is going to become one where we have this plus sigma identities, sigma squared identity minus corresponding terms here. So actually this one doesn't even have a correction because these are cross covariants, and this just changes the main diagonal. But here we have it again. And this actually becomes a penalized least mean square space. So if you've ever computed pseudo inverses, or if you had to invert a matrix, you add a little bit to the main diagonal, you're effectively doing this. You just didn't know it. Maybe you knew, but so now what we effectively did is something a lot deeper. So if you look at this equation here, right? We had epsilon, we had t. And each of them have their own distribution. We take the sum, and then we go for a characterization of those y's directly. So in order to get that, we had to integrate out this epsilon. So that helped us get rid of one of the unknown, in other words, latent variables in our model. We're going to see this effect over and over later on as we work with probabilistic models later in this class. We're going to spell out interesting models, and then we're going to integrate out some pieces in order to make things computationally more attractive. This is just the first case. And this was really easy. We didn't see any integrals because I just said, well, if this is drawn from that normal distribution and epsilon is drawn from that term, then the sum of both is given by that. But what happened behind the scenes is that somebody solved this integral. Probably Mr. Gauss did.
So Pyi given xi,
so, well, actually, these y's only really depend on those t's, and the t's depend on the x's. So this decouples.
But t depends on x and y.
Yes. So y only really depends on t. So I don't need to be able to look inside the argument of t in order to know how y behaves. So that's just to make things easier. Now, if y were to depend on x as well, you would actually get heteroscedastic regression. And I'm going to show you an example of that later on. And I'll show you that you can do that as a nice convex problem.
What exactly is t of x?
So t of x is the random variable that I might want to estimate. And I'm not observing that one directly, but I observe it with some added noise, and it's called psi on my slides and epsilon on the whiteboard.
And what's x?
X is photograph, a web page, a user profile, basically whatever covariate you might want to throw at it. So you might want to do some regression estimation, like amount of dollars donated to my political campaign. And X is basically information about the neighborhood and whatever. And so if I were to do this, I could try to build a regression estimate of, in which neighborhoods I should particularly go and campaign for, and how I should tailor my votes in Congress to make sure that these neighborhoods donate the most. You could do that. So X is basically any set of covariates. So we have a regression problem. By the way, thanks for the question. Any more questions? Okay. So, let's just make it a little bit more concrete. So here's some data. That's what I'm observing. This is X, this is Y. Now, I can just plug in the predictive mean. And if you just, use the math that we saw before, this just gives me K of X and capital X transpose. So capital X is the training set. And then here we have the kernel plus, the correction on the main diagonal. Entire thing inverse times Y. And that, solves the regression problem. Try and see what I can make myself a nice long stick from whiteboard markers, but I think I'm out of luck today. They're all gone. Okay, now why is this regression estimator interesting? Well, yeah, sure, I can regress fairly well, as you can see it's not an interpolation but a regression. Then an interpolation would go through all the points. By the way, for your project presentation, this would be a bad slide, right? It would be a bad slide because it's not really legible very well in the back. So light green on a white background is not good. So don't do what I do, but what I say, right? Here's the variance. This is basically just, we know that at any new point, of course we have variance sigma squared, which that's the additive noise. This term here. We also need to get a handle on those t's, right? And that's basically what we had with k of x, the entire matrix inverse k of x. And so if you add or subtract, the square of the variance from the mean, you get this nice dotted upper and lower envelope. And lo and behold, well, it actually fits the data very nicely. And what we just recovered is that we've realized, hey, we can actually estimate the sine function from a few points. Well, that's not such a big deal. And you can try it out for another set of points that were randomly drawn. An interesting thing that you can see here is this red line goes up on the boundaries, right? So first of all, so this is the amount of variance. So first of all, even where I see a lot of data, it never really goes to 0, because I'm assuming that I have some additive noise. And that's reflected in the fact that, these instances are actually noisy. However, over here, where I have next to no data, well, my variance will go up. Because I really don't know how this function will continue. And here I simply happen to get reasonably lucky to see 2 points, and they pin things down. The variance is reasonably flat throughout. So to just show you the algebra again, so we just add some noise to the kernel. Then the predictive mean and variance are exactly what we had before, right? Just that our kernel now looks a little bit differently. And then I can do a point-wise prediction. It's just the future variance. And just run the algebra through and you're done. So it's really just, a matrix inverse. That's all that's really going on behind all these equations here. So if you've ever computed the matrix inverse, this should not look scary to you. Even though, of course, each time I do this, I either have to re-derive the algebra or I just look it up. Okay. Any questions so far? Yep?
How do you choose the kernel?
Great question. Terrific question. Okay, so there's a couple of answers to that, and you could probably teach an entire class just on that subject. Okay, so the first thing is you want to be a good engineer. As a good engineer, you're going to look at your problem and determine what a good covariance structure is for your observations. And then you use that information to come up with, a kernel. That's one way. And of course you want to make sure it's positive semi-definite and all that. The other thing is you could actually measure things. So for instance, if you have audio signal for speech or whatever, you could just compute autocorrelation functions. And that might give you a good idea of what things should look like. You might have some, biological engineering knowledge or whatever about the uncertainty. You could also use that. Now, if all of that fails, and most likely it would, you need to adaptively adjust the kernel based on the data. Now, there's a couple of simple hacks that will work really well, and there's a couple of more principled things. The simple hack is if you want to have a nonlinearity, you basically pick a Gaussian RBF kernel, and you just pick the scale of the Gaussian RBF kernel in such a way that the average distance between 2 points is commensurate to the scale of the kernel. The reason for doing this is because you want to make sure that you neither end up with a matrix that's just diagonal, which means each instance is only similar to itself, nor a matrix that's entirely flat and constant, which means everything is perfectly similar to everything else. And picking the kernel width to be order 1 of the median of the pairwise distances will do the trick for you. Yep.
What's a good way to estimate in that potentially unrealizable kernel space the distances again?
Okay, so we are actually going to do 4 or 5 slides just about Hilbert spaces and so on in a moment. But let me quickly show you the equation, because it's actually really simple once you start thinking in those weird kernelish ways. So here's what happens. And by the way, these kernels here and the kernels for SVMs are related insofar as they are the same function, but they mean entirely different things in both cases. And that's not always really trivial to distinguish. So the issue is that it's very difficult in probability theory to define distributions over infinite dimensional objects. It's really nasty to normalize them properly. Whereas in the SVM risk minimization point of view, you don't necessarily care about the dimensionality of the underlying space. You only care about the complexity of what the space realizes. Now, as a good Bayesian, you get around it by just saying, well, I'm only going to evaluate my Gaussian process at these points, and so now for a finite number of points, I have a normal distribution, and so everything is fine again. But that's a fairly subtle distinction between the more probabilistic viewpoint and the viewpoint of we have functions in a Hilbert space that are properly normal. So here's what we get. Remember what we had is that phi of x dot phi of y was just the kernel k of x and y, right? That was our standard trick, how we introduced the kernel. Now, if I want to compute the length of phi of x, and the length of phi of x, well, is that, right? Squared length, just the norm squared, which is nothing else but the inner product between phi of x and phi of x. Right. Now we know how to compute that, because that's exactly what we did up here. So this equals k of x and x. Now here's a really bizarre instance of this. If we have a Gaussian RBF kernel, and our kernel looks as follows: k of x and x prime is e to the minus 1 over 2 sigma squared or whatever norm of x minus x prime squared. So from that it follows that in this specific case here, k of x and x is 1. Because the argument of the exponential vanishes. So any kernel that only depends on the distance between its arguments will have that property, that k of x and x is a constant. So what does that mean? It means that we are mapping whatever original space we had onto the surface of a ball. It sits there somehow, of a unit ball in some infinite dimensional space. So that's why last week, when we talked about single class SVMs, I showed you that the problem of chopping off a cap from this ball is equivalent to finding the minimum enclosing ball of this. So that was single class SVM last week. And in RBF kernels, that's exactly matched. Any more questions?
Why is that infinite dimensional?
Well, it doesn't have to be infinite dimensional, but for the RBF kernel, there's, for instance, a proof that any kernel matrix that you write out, where no 2 points are identical, will have all non-zero eigenvalues. You can see that a little bit by using the fact that the inner product, that the convolution of two Gaussians is a Gaussian, right? Now, it basically means you have an inner product in an infinite dimensional space between two Gaussians. The convolution is exactly what gives you that. So, that's an example. More generally, there are kernels that are called characteristic, which have all those nice properties that basically you won't run into trouble with, with running out of dimensions. Okay. So now let's have a look at some conditional models. Yes.
Just to make sure.
Yeah.
Earlier you had the notation with big X and big X prime.
Yes.
Could you describe explicitly what?
Oh, okay.
content is?
Okay. So I was being lazy here. So big X is the entire set, and I was just overloading the kernel in the way how you would overload your functions in C, maybe, where rather than feeding in individual items, you feed an entire set, so you get an entire matrix out of it.
So you're saying it's the individual xi stacks?
Yeah. So basically, K of big X and big X would be a matrix, would be in R, n by n, where the entry K, big X and big X, the ijth entry, is basically just little k of xi and xj.
And then X?
And then K of capital X and little x simply is a vector. So if I feed in single instances on both ends, I get a scalar out. If I feed in sets on both ends, I get an entire matrix out of it.
And then earlier in your slides you had the visual example. Can you go back to?
Yep.
And at the top you said the mean one slide. Yeah,
Yep.
there. So there you had, I guess, your previous notation would have been big X times.
Well, no, this is actually for any given point.
Yeah.
For any given little x, like any point here, it's a vector transposed. Now here we have a matrix plus something in the main diagonal, inverse times some vector again.
And
So the y's are now a vector.
my issue is that previously, on a few more slides earlier,
Uh-huh.
was a leading term before that big K.
Yeah, so the difference is that I just set the mean to 0.
One there. One slide forward.
There?
Or other
Yes.
direction. I guess. Sorry. There.
There.
A mu bar, so you have that big X prime transpose big X times
Yeah.
big X transpose.
Now, okay, so this
What's
is
that
basically...
big X within this?
Yeah, okay. So T turns into Y.
Yeah.
This is the first kernel. That's the second kernel. So that's basically K of little x and big X. Because I'm now just interested in predicting the value at, location little x. This X transposed capital X becomes, covariance matrix plus, whatever I add to the main diagonal, inverse. And here, these are the observations. So it matches up exactly. So the difference is that the T's are, so in this case, when I'm observing that I'm assuming that I'm actually observing the T's. Later on, I'm assuming that I'm not observing the T's directly, that I basically, have the X's. Given the X's, I draw the T's from the X's, and then I draw the Y's given the T's. That's the idea. So suitable notation, we would have that we maybe draw independently all the xi's. I make a box around it just to denote that this is a plate. Now, dependent on all of those, I draw the t's. This is now the vector. These are all of the t's at once. And then based on that, I draw the y's. And these now depend on each of those ti's. But the t's are drawn jointly. That's what couples everything. That's basically where the correlations between different locations come in. You could also view that as follows. So this is the parameter notation of this, where I basically have the xi's. I draw the yi's, conditioned on the xi's, and I have some parameter w. So this is basically inner product representation. And that's not entirely accurate in the Gaussian process case because I really don't necessarily have this parameter w, but in practice it's a good kludge to see what's meant. Okay, yep.
Can you please explain again the difference between t and y?
So t is latent, y is observed. Y is the noisy version of t. Now we're going to see exactly that in a lot more detail here. So let's just briefly recall exponential families, right? So this is what we used to do. P of x parameterized by theta is e to the phi of x of theta minus g of theta. This ensures that the probability sums up to 1. And then if I want to compute expected values of those phi of x's and variances of them, I just take derivatives. And, well, that's nice and convex. Right? Now what I'm going to do is, I'm going to do the same thing for conditional exponential families. Okay, so what's the only thing that changes is that now rather than a distribution over x, I get a distribution over y given x, and some parameters theta. And, well, I now just have some feature map of x and y jointly in a product with theta minus g of theta given x. And now this g of theta given x is just, again the normalization, where now I only sum over the y primes as opposed to the x's. And that might make my life a lot easier because the y's could, for instance, be just, binary random variables. They could be just plus and minus 1. Or they could be, an ontology where I have, maybe 200 different outcomes. Whereas the x's might be things like an entire web page, a user's behavior, or anything like that. So that's why this gets a lot easier. So to get the key idea across, and this is something of a recipe that for some time was fairly straightforward to actually generate scientific publications from. You basically take the Gaussian process, index y, x, and y, and then you plug in different choices of y. And if nobody had picked your choice of y before and you figured out how to compute the normalization, you would have a new algorithm. So, simplest case, binary y's. Well, these we've actually already done. So if y is 1 or minus 1, then estimating a 1 or a minus 1 given x, well, that's a classification problem, right? After all, for classification we want to know, is it ham or span? Is it apples or oranges? If I allow y to take a more diverse range of outcomes, I get multi-class. Okay, still very boring. Here's where it gets a little bit less boring if I make y to be an integer. Then I can, if I normalize suitably in the y's, get a Poisson regression out of it. And the good thing is, it really only requires 2-3 lines of code change to get there. Because all you're doing is you're just messing with phi of x and y. You pick a different phi of x and y, you get a different estimate when you're done. Now, one of the really cool things is you can get heteroscedastic regression as a convex problem. So I'm just stressing that because, yeah, people seem to forget that fact all the time. So as people publish algorithms about something that's not a convex estimator, and then they get awards, and at the same conference we published a few years before that a nice convex scheme. Yeah, people just forget that occasionally, that they're actually simple estimators for heteroscedastic regression. So I'm going to show you a little bit how that works. The idea is very simple. You basically, when you take a Gaussian, well, you have the mean parameter and you have the covariance parameter, right? So if you have the mean and the covariance parameter, and we have an exponential families model, there's nothing to prevent us from estimating mean and covariance as conditional on x. If I estimate mean and covariance as conditional on x, I effectively get a heteroscedastic estimate. In other words, an estimate where the variance is allowed to be variable as a function of the location. So this is a bit different from what we saw before for a standard GP regression, where, yes, our uncertainty also was variable, but the variable uncertainty arose from the fact that we simply didn't measure things everywhere. Here, the variance in uncertainty arises from actually observing data and seeing that some observations over here are a lot more noisy than over there. So that's an important distinction. On top of that learned uncertainty, you still have the fact that you don't really measure things everywhere, but at least you can also learn how sure you are about things. And then if we have sequences, this gives us conditional random fields, and we're going to look a lot at them later, maybe next week or the week after that. So the key point is that our Gaussian process is now in those latent variables. Regression just happened to be a really nice special case where we can integrate everything out. What happened is actually that people started with Gaussian process regression and didn't realize that this was a particularly nice case, and they got stuck. And it took a few years until people figured out that they could do classification, and that was just a different objective function, and then actually tying it all up to exponential families took a couple more years. So in hindsight, it's very simple. Let's just take a simple conditional Gaussian model. So if we just assume that, you know, we have a fixed covariance, we just want to get the mean, well, then, you know, this is all we get. Sorry, this is actually an exponential distribution. It's just exponentially decaying, nothing else. And then you just optimize with it. So let me show you an example. Okay. So here we go. So finally label space 1 to -1. And without loss of generality, I can actually, you know, because now I have this Gaussian process not just indexed by x, but I have it indexed by x and y. And without loss of generality, I can actually center it to be t of x and y to be y times t of x. So t of x and y is, you basically got to think of that as phi of x and y plus theta. That's your connection. So the reason why I can center it is because, well, you know, at the end of the day, assuming that the, you know, positive or negative class aren't anything special, I ought to be able to just flip the signs on everything and essentially get the same equations back, right? Furthermore, you can see that in the exponential families model, since we have that normalization, a constant offset to all terms doesn't really change our model. So therefore, I can get rid of one dimension. So if I have a 10 class classification problem, I only really need 9 dimensions to specify it, right? I mean, everybody knows that. If I know the probabilities of 9 out of those 10 events, I know the probability of the last event. And that's effectively what's happening here. Now, the log likelihood, so P of y given t, is just, you know, log of, this is our normalization, e to the t plus e to the minus t, because we basically plug in plus 1 and minus 1 in here, minus, you know, y times t. That's our, you know, sufficient statistic term. And then all I do is, I just, you know, divide by e to the minus y times, I multiply by e to the minus y times t, those two terms here. Now what happens is, you know, since we have 1 and minus 1, in the case where y equals 1, then this becomes, you know, 2t, 2y times t, and here we get the 1. In the case where y equals minus 1, this becomes 1, this becomes e to the minus, it becomes e to the y times t, to y times t. In other words, this expression here. Right. So, this, up to a factor of 2, is exactly the logistic function that we all know. That's what we introduced last week. And then you can, for instance, do maximum posteriori estimation. So you basically maximize the posterior probability with respect to t, and you get a nice standard convex problem back. Now this ought to look very familiar, right? Because it's just this one here, right? This was our step loss function. This is the logistic. And this was the Hooverized soft margin as soft margin. Right? So that's where this came from, the blue curve. Okay. So this actually tends to work fairly well. If you look at clean data, yes, it separates things, and I just added a margin of separation. I basically just, you know, picked the line where the score in the exponential was 1 or minus 1, and I just drew that line. Could have picked any other one. And if I have noisy data, then, well, okay, the margin just gets a little bit smaller, and there are some points that are not correctly classified. Okay, any questions so far? Now it's going to get a little bit more technical, so we're going to do heteroscedastic regression. If you think about it, so GP regression has a variance estimate that's independent of the observed data. So in a way this is great if I want to do experimental design, like I want to measure the weather in various weather stations. If I can assume that, you know, my observation distribution is drawn from a GP, I don't actually need to measure things. I can completely ignore the landscape or whatever, or at least the actual measurements, and just go and determine whether, you know, where the meteorological stations are set up. But of course that's garbage, right? Because we know that in some locations there's a lot more variability in the observations than in others. So let's actually estimate the variance at the same time as estimating the mean. So you can do that very easily. So this is just our normal distribution, and we already all saw how you get your sufficient statistics, right? Who hasn't seen that equation yet? Okay, so this is what we did, I think about 2 weeks ago when we talked about exponential families. We basically had as our sufficient statistics, you know, x and, you know, minus 1/2 xx transpose. And this is the normalization that ensures that, you know, a Gaussian integrates out to 1. And then I just, you know, do proper variable substitution in terms θ2 and θ1 to get an inner product here. And now the normalization is this rather ugly looking term, which however happens to be convex. This is not a term that I could dream up. I would say very few people would be as ingenious as to dream it up, but by just cranking the handle, you get that normalization right away. Now what I'm going to do is I'm going to make θ1 and θ2 variables, and I'm going to estimate given data. So here's what we have. Basically phi of x and y, so that joint feature map is y times phi 1 of x and y squared times phi 2 of x. So the first term essentially takes care of any linear, and the second one any quadratic dependency in my exponential. And if I want to write out the kernel, I'd get what I have in the next line, but I don't really care very much about the kernel here. But that would be basically the Gaussian process on the x and y pairs. Okay. So now, if I just look at the log likelihood, you get this, well, fairly atrocious looking mess here. This fairly atrocious looking mess, I mean, let me parse it for you because it's a big mess here. So this is, well, this is basically nothing else than the normalization. So that's basically the theta 1 transpose theta 2 inverse theta 1. Vector matrix inverse vector. And that's the log determinant term of the matrix. So that was that here. It's this here, right? Theta 1 transpose theta 2 inverse theta 1. That's the log there. Now this is our linear term, already expanded in terms of kernel functions. And, well, with the corresponding y's, and here's a little bit more normalization to ensure that nothing diverges. So, you'd be crazy to remember that formula, but don't. The one thing that I want you to remember is how we get to this formula. Namely, we simply take a Gaussian, possibly multivariate, look at the natural parameters that correspond to the mean and covariance. Make them drawn from a Gaussian process. And then we happily go away and optimize. So the nice thing is this problem is actually convex. Unlike any other heteroscedastic Gaussian process regression problem that I've seen, this is actually computationally very attractive. The other thing is, you see this ugly expression here, well, you probably can't, it basically has some little, it basically means that the covariance must never become negative. The way how you fix it is actually by adding a constant offset to your covariance function. So it's not so terrible. And the log determinant is what in optimization speak is called a log barrier in this case. And that basically ensures that we never pick a negative variance. So we always stay nice and feasible. So let me just show you an example. So this is basically for some mean estimate, and the blue curve is what we estimate, the green curve is what we actually have, and then with covariance added, that's what you get. Now the interesting thing is that it also manages to estimate the uncertainty fairly well with the data. So the red curve is the true variance, the blue is the inferred variance. So we are not only estimating what the value is, but also how certain we are about things. In terms of computation, it's a bit of a mess, and I would say you're probably best advised actually reading the original paper. So I'm not going to inflict all those details on you, but you basically, what you do is you basically come up with a low-rank expansion, you use conjugate gradient for the convex but non-quadratic objective function and restart a few times. And you really avoid, as much as you can, ever computing the second derivative of this entire expression, because you wouldn't have enough memory to do so. You have a question?
So to get a picture, this is just a
That's a toy
way
example.
of doing MLE on sufficient statistics
It's
in kernel space.
It's a maximum posteriori estimate because we impose the Gaussian process on the parameters.
Oh, okay, so we have a price of
So
that estimate on parameters in kernel space.
Yes. So this is not an MLE. An MLE would be one where we don't assume anything specific about the distribution over our unknown latent parameters. This is map because we actually assume that they are jointly Gaussian. And yeah, I mean, basically there are efficient tricks how to compute it. Let me show you a little bit what happens for a bit more realistic data. So this was, okay, there is no exact model, but basically what happened is this was radiation data for, you know, some, I don't know how many square kilometers it was. Yes. Yeah, basically, yeah, this is about 100. It's about 1,000 kilometers or so, and somewhere in the middle there, a nuclear reactor emitted radiation. And what you want to do is you want to estimate the radiation levels. And the standard Gaussian process is pretty awful because essentially, okay, this is where the reactor exploded, and everything here is affected, and it also curves up things at the boundaries, which is completely nonsensical. The radiation is in here. If you have the heteroscedastic process, it actually fits it very well. It basically, okay, this is a slight artifact here where it pulls the coal down further down, but it basically gets it right that this is where, you know, the disaster happened, and out here things are free. And to show you in terms of the variance, well, this is the uncertainty it has about the data. This is all inferred. This is not modeled. So the difference is that basically it learns that, you know, throughout here it's fairly sure that nothing is happening, because, you know, unless you have actually, you know, a nuclear explosion, well, or, you know, some reactor going berserk, well, you don't see more than the background radiation. But right here where things went really bad, it learned it very quickly that things were bad. So that's the kind of things you can do efficiently with convex optimization, actually also at scale. So what I hope I showed you a little bit is, well, the kernel trick, a bit of SVMs, and a bit of GP estimation. So I think we can probably take a short break and then reconvene in about 5 minutes or so.